as we turn our attention to Chapter 13, Equilibrium, you're going to find that there are a lot of details here at the beginning, and you are going to find also that this concept of equilibrium and everything we can calculate with this concept is going to be as central to chemistry as the concept of the mole. But before we start to look at all the practical uses of equilibrium, such as understanding how buffers work to mitigate changes in pH, either in the living cell or in large ecosystems, or as we look at the effects of pollutants in the air and how temperature and pressure and things like that cause changes in the gas concentrations that cause certain types of pollution. All of these things that we're going to discover that equilibrium can explain to us, there are a few details we need to understand. And the first thing I'm going to take you to is this website that describes a little bit about equilibrium. Almost all chemical reactions are reversible. In other words, wasn't quite done with that. Both the forward and reverse reactions will occur. When the forward reaction is happening at the same rate as the reverse reaction, the reactions are in equilibrium. Now, this happens in chemistry, but there are a lot of applications outside the field of chemistry, including the Nash equilibrium. If you've ever watched the movie A Beautiful Mind, John Nash became famous for his equations describing equilibrium systems in economics and games and things like that. Well, what is equilibrium? Imagine you had someone who was up to no good, and they took a large shovel and began filling in a well by digging a hole next to it and dumping the dirt into the well. So the large shovel can move a large amount of dirt. So at first this person deepens the hole rapidly. Now the owner of the well angrily begins to use a smaller shovel to empty the new dirt out of his well and back into the hole. At first, because the shovel is small and the dirt has to be moved all the way up from the deep well, the well owner isn't able to match the pace of the miscreant, and the well continues to fill despite his best efforts. However, as the hole deepens, the troublemaker with the large shovel has to reach further and further down into the hole to dig the hole deeper, slowing the progress. And in contrast, I keep losing my place here, but you can go to this website. You have the link here on our website. As the well is being filled, the owner with the small shovel has to move the dirt a smaller distance, so she is able to empty her well and fill in the hole. Here we go. Let's see how this works now. So if we speed this up, eventually the rate at which the well is being filled is equal to the rate at which the well is being emptied. Here, the depths of the well and the holes have reached equilibrium. So this system is at equilibrium. No matter how long we watch it, as long as they keep using the same system and the temperatures don't change and all of those kinds of things, the opposite reactions are occurring at the same rate. That is equilibrium. The filling rate, you'll notice, is equal to the emptying rate. Chemical reactions behave in a similar manner. When the rate of the forward reaction is equal to the rate of the reverse reaction, the rate has reached equilibrium. The forward reaction becomes slower and slower as the concentration of the reactants drop, and the reverse reaction speeds up until they reach equilibrium. And we show this equilibrium with arrows pointing both ways. The rate law for the decomposition of N2O4, the forward reaction, is first order in N2O4. The rate law for the formation of N2O4 from NO2, the reverse reaction, is second order in NO2. At equilibrium, the rates of the forward and reverse reactions are the same. This allows us to create a new constant, the equilibrium constant, K. Now, this particular way to think of this mathematical solution works only if we have elementary steps. But the equilibrium constant that you're seeing here at the bottom of the screen is we can get this equilibrium expression from any reaction that we're going to look at. Remember, just because the rates are equal, though, just because the rates are equal at equilibrium does not mean the concentrations of the reactants and products are equal. In most cases, they will not be equal. So the equilibrium constant for any reversible reaction is related to the concentrations of the products and the reactants. At equilibrium, the equilibrium constant is equal to, so this K value that you're seeing here is a constant that we can calculate. It's the concentration of the products raised to their respective stoichiometric coefficients divided by the concentration of the reactants raised to their respective stoichiometric coefficients. In other words, we have C raised to the C power, D raised to the D power, divided by A raised to the A power, and B raised to the B power. This is known as the law of mass action. The equilibrium constant in terms of molar concentrations is often written with a capital K and a lower c to distinguish it from an equilibrium constant that might be in other units. Another equilibrium constant is Kp, and this is often used for reactions involving gases because Kp is the equilibrium constant in terms of partial pressure. It is important to note that Kc and Kp are not equal, although there is a way to make a conversion from one to the other. So I would encourage you to go to the website and practice these 3 quiz questions.